Hi students, welcome back to my YouTube class. In the last class we have studied T0 space and T1 space and solved some examples and proved some of the theorems on T0 space and T1 space. Okay, now I am going to discuss T2 space. T2 space is also called as Hausdorff space. Definition: let X tau be a topological space, then X tau is said to be T2 space. For each distinct pair of elements X and Y, there exist neighborhood N and M such that X is a member of N, Y is a member of M, and their intersection N intersection M is empty. X tau is a topological space. X tau is said to be T2 space if for each distinct element of different elements of X and Y, there exist neighborhoods N and M such that X is member of N, Y is member of N, and N intersection M is empty. Example: let X equals set of 1, 2, 3 and tau equals set of X pi set of 1, 2 set of 3. Then show that X tau is not a Hausdorff space, not a T2 space. Here X is given, X is set of 1, 2, 3 and tau is given, tau is set of X pi set of 1, 2 singleton set 3. Here for A and B distinct elements of X, for any two distinct elements of X, there is no distinct neighborhoods. So given space X tau is not a T2 space, not a Hausdorff space. Okay. Next example: show that an indiscrete space consisting of at least 2 points is not a Hausdorff space. Okay. Here an indiscrete space, X is an indiscrete space consisting of minimum 2 points is not a T2 space. Let tau be an indiscrete space on X consisting of at least 2 points. Okay, then we have tau equals set of X and pi. This shows that there does not exist any pair of non-empty disjoint open set. So X tau is not a T2 space. Next example: a very discrete space is Hausdorff space. Let X tau be a topological space, and X, Y are the members of X, be arbitrary, such that X and Y are not equal, they are distinct. Using definition of discrete space, we have singleton set X, singleton set Y are open set. Obviously their intersection is empty, they are not equal and they are open set, then their intersection is empty. This implies X belongs to singleton set X, Y belongs to singleton set Y. Hence there exists disjoint open set singleton set X and singleton set Y containing X and Y respectively. Thus X tau is Hausdorff space. Okay. Next theorem: each singleton set in a T2 space is closed. Okay, let X tau be a Hausdorff space. Since X is T2 space, implies X is T1 space. This implies singleton set X is closed for all X belongs to X. Hence, each singleton set in a Hausdorff space is closed. Next theorem: prove that every subspace of a Hausdorff space is T2. Every subspace of a T2 space is T2. Okay. Let X tau be a Hausdorff space and Yu be a subspace of X tau. Or let Y1 and Y2 or any two members of Y such that they are distinct, they are not equal. Since X tau is a Hausdorff nothing but T2 space, X tau is a T2 space. This implies that there exist disjoint neighborhoods N1 and N2 of Y1 and Y2 respectively. Okay. Now using the definition of neighborhood, there exist tau open set G1 and G2 such that Y1 belongs to G1 and Y2 belongs to G2, and G1 intersection Y1 and G2 intersection Y are distinct U neighborhoods. Hence YU is also a T2 space. Next, theorem, a very finite Hausdorff space is discrete. Okay, a very finite Hausdorff nothing T2 space is discrete. Let X tau be a finite T2 space. Now we have to show that this is discrete. To show that X tau is a discrete space, since X is T2 space, now implies X is T1 space, because every T2 space is T1 space. Singleton set X is closed subset of X for every X belongs to X. Then A equals set of A1, A2 and so on An be a finite subset of X. Then A can be written as singleton set A1 union singleton set A2 union and so on union An. This is finite union of closed set. We know that finite union of closed set is also a closed set. Therefore A is closed set. Okay. Thus, every finite subset of X is closed because X is finite and A is a subset of X. This implies X minus A is finite. This implies X minus A is closed set. X minus A is closed set, nothing but A is open set. Hence, every subset of X is closed as well as open. Therefore, X is discrete space.